Is the presentation visible? Okay, let's start today's session. Welcome to the sixth week's tutorial session of EMI, EMC and signal integrity. So, in the last week, we discussed about the radiated emission caused by differential mode currents and common mode currents. We also saw that the radiated emission caused by differential mode currents is not very detrimental in the sense that they are subtractive in nature. As in for differential current, the current directions are opposite in the two wires. Therefore, the the emission caused due to differential mode currents, they are subtractive. But in for common mode currents, the field is additive. So it is more detrimental. We also solved numericals to find out what is the electric field caused due to differential mode current and electric field caused due to common mode currents. Okay. And in the towards the we also discussed about current measurement, how we measure a current with the help of a current probe. What is the impedance characteristic of a current probe? All these things we discussed. Today's topic is today we will be talking about radiated susceptibility models. There are various models. The main topic of discussion would be the per unit parameters, per unit inductance and per unit capacitance of a two-wire system. So if you have read about transmission lines, you must have encountered these terms: per unit inductance, per unit capacitance, characteristic impedance, ZC, which is basically root L by C, where L is the per unit inductance, C is the per unit capacitance. L by C, okay? All these things in the undergraduate power system course you must have heard. So for radiated susceptibility also, we will see how to determine these LC values for a two-wire system and also for a coaxial cable. Okay. And obviously there will be some numerical problems that we will solve. Okay, so let's see the first question. Consider the following statements. Characteristic impedance of a transmission line depends on per unit length capacitance and inductance. This is true. We just saw that the characteristic impedance ZC is equal to square root of L upon C. So characteristic impedance is definitely dependent on per unit length capacitance and per unit length inductance. For a homogeneous medium, the product of per unit length capacitance and inductance is a constant. Okay, so that is also true. So LC is equal to mu E. Okay, where mu is the permeability of the medium and E is the permittivity of the medium. Okay, so this is a constant. This is a constant. Fine. Statement B is also true. So both statement A and B are correct. Let's see the next question. A two-way transmission line in free space carrying constant current has a center-to-center separation of 100 mil. Considering wire diameter to be 5 gauge, determine the per unit length inductance of the line. So as I said earlier that we will be calculating the per unit length inductance and capacitance of a two-way transmission line. Okay. Two-way transmission line. There is some voltage source Bs. Before solving the problem, just let's just discuss a bit about this is from the lecture notes only. I will just explain a bit so that it is easier to understand the problem. Right. So this is basically a two-way transmission line where this side the current is going inside and from this side it is coming out. Right. This is a cross. This is a dot. So if you are obviously familiar with right hand rule. So if the current is going inside the plane, then the magnetic field direction will be like this. And if the current is coming out, then it is like this. So in this portion, the magnetic field is additive. Okay. And what is the flux? Flux is BT dr, integral BT dr. Okay. And where this BT is coming from? This is coming from here. Suppose there is a circular, this is the cross section of the conductor, and HT, that is the magnetic field intensity, it is tangential like this, right? And R is the radius of this conductor. If you know Ampere's law, what does it say? It says that integral HT dl is basically I enclosed, right? That is Ampere's law. You have heard, right? So integral HDL, that is basically ampere turns. HDL means, and that is equal to I enclosed, right? So HT we can find out. HT is what? Then I enclosed by DL. What is DL? This is the circumference. That is 2 pi r. So HT is equal to I enclosed by 2 pi r. I is the current that is flowing through the conductor. So if you are taking the whole cross section, then the total current is I enclosed is I, the current that is flowing. Ampere per meter is the unit. And what is B? B is nothing but mu HT, right? So if you just multiply mu with this, you will get B. That's what is written here, mu I by 2 pi r. This is BT and then dr. We are integrating this. The range is from R1 to R2. R1, R2 may be some two different distances. So this is the expression. Now if we are considering two conductors, so we will separately take the flux of both of them and then it will be we will be adding them. Why? Because in this portion they are additive, their direction is same. That's what is done here. This is psi m1 plus psi m2. So mu I by 2 pi ln. This is S minus, suppose this is Rw1, this is Rw2, the radius of the conductors. So this is S minus Rw2 by Rw1. And then again for the other conductor, this is S minus Rw1 by Rw2. We will take some assumptions. What are the assumptions? That S is much greater than Rw1 and also it is much greater than Rw2. Obviously, the separation between the two conductors will be much higher than their radius. So this assumption is justified. So this parameter over here, this we can approximate at S minus Rw1 is basically S and S minus Rw2 is also S because this is negligible compared to S. Now what do we get? S square by Rw1 by Rw2. And if the radius are same, Rw1 is equal to Rw2, then here you get A square by Rw square. the two you can we can so 2 can come out of this logarithm. This becomes mu I by pi ln S by RW, Henry per meter. Okay. And if we represent it in terms of microhenry, then 0.4 ln is by Rw microhenry per meter, right? So the all this comes from the basic laws: Ampere's law, Faraday's law. For the Faraday's law, then Maxwell's equations. Okay, the basic from these basic laws we can find out what are the expressions. Okay, so now we can find out the answer, right? This is the final expression for per unit length inductance. I hope you understood how we are coming to this expression. And when we were representing in terms of microhenry, it was zero point 0.4, zero point 0.4 ln S upon Rw microhenry per meter. This is just a more simplified version of this because mu, we are assuming it is mu naught. Mu naught value is 4 pi times 10 power minus 7. Okay, so pi and pi gets cancelled. That this becomes 4 multiplied by 10 power minus 7. And as we are representing in microhenry, so this is 0.4 ln S by Rw. Okay, so what is S? S is equal to 100 mil. This is kind of a new unit. We generally don't use mil, but this is a common unit used for distance. Okay. We will convert it to centimeter, suppose. So 100 mil, first to inches, then in centimeter. So this is 0.001 multiplied by 2.54. 2.54. Okay. 2.54. This is in centimeter. So this is 2.54 centimeter. What else? RW, the radius of the wire. That is 5 gauge. 5 gauge is basically equal to 0.25 centimeter. That is 0.02, 0.25 millimeter. That is 0.025 centimeter. Okay. So now if we calculate it, we get the value. Let's see what we get. 0.54 divided by 0.025. Sorry, this is 0.254. So this is 0.254. Okay. We are getting 0.927 microhenry per meter. 0.927. Okay, let's see. Option B. Okay. Microhenry per meter. Please observe the unit, because if suppose it is not in microhenry, it is in nanohenry or some other unit, then you will have to uh, calculate accordingly. Okay. Microhenry per meter. Let's see the next question. Consider a two-way transmission line in a homogeneous non-magnetic medium with dielectric constant 1.5 carrying a constant current. If the inductance per unit length of the transmission line is 1 microhenry per meter, determine the per unit length capacitance of the line. Okay. See, first of all, they have told that homogeneous non-magnetic medium. That's why we can take mu is equal to mu 0, mu naught. Because this is a non-magnetic homogeneous medium, we can take mu equal to mu naught, and dielectric constant is given. So this permittivity is basically ER epsilon R and epsilon multiplied by epsilon naught. And this constant is given, relative permittivity is given 1.5. Right? 1.5 carrying a constant current. And inductance per unit length is also given 1 microhenry per meter. Okay. So as they have already told that this is a homogeneous non-magnetic medium, we can easily say that LC equal to, that we saw, LC is equal to what? Mu E, mu epsilon, right? This is basically mu naught, then epsilon R and multiplied by epsilon naught. Okay, this we can tell. C is what? Mu naught epsilon naught R, epsilon naught by L, right? Let's see. 5 times 8.854. Okay, so mm, so this is 4 pi times 1.5, then 8.854. This is there with this we have 10 power minus 7 and here we have 10 power minus 12. So here we have 10 power minus 7, here we have 10 power minus 12 with epsilon naught. If we want to represent it in picofarad, then we will just leave alone the 10 power minus 12. So this basically becomes 1 166.89, right? So by 10, so this will become 17, almost 17.11. It's approximately 0.11 is, so think so option D. Okay. Just a minute, huh? Yeah. Okay, so let's resume. So the next question says that a 5 gauge wire is at a height of 50 mil above ground plane carrying constant current in free space. Determine per unit length inductance of the line. So there is a transmission line which is at a height h from the ground, suppose. Okay. And we need to find out what is the per unit length inductance. Here, what concept is used is the concept of image. Suppose this is an isolated wire, but what we can do is we can suppose we can assume there is a exact conductor of same dimensions just at the opposite of ground. So if this is h, this distance is also h. And now we can apply the two-way transmission line concept over here. Okay, actually it was one single transmission line, but here also we can apply the two-way transmission line concept. Okay. See, here what we do is, if there is a transmission line and with respect to ground, obviously there will be parasitic capacitance, right? There will be parasitic capacitance from this wire to ground. And as we are assuming there is another conductor, from here also there will be another capacitor to ground. Okay. And they are identical. So if this is C1, this is also C1, right? And they are in series. Then what is the equivalent capacitance? The equivalent capacitance CEQ is C1 by 2, right? C1 by 2. So that's what is written here. C1 is 2 times C2. So C2 is basically C equivalent. Okay. C1 is twice of C2. And then again, if you just apply the basic laws, you can find out this expression. Okay. You can find out this expression. And as we know, multiplication of L and E is the multiplication of mu epsilon. So we can easily find out what is L. Okay. Right. So how does this C comes? So this E electric field is basically equal to Q by 2 pi R. And what is V? V is integral EDL, right? Integral E dot dl that we know. Suppose there is some range R1 to R2. So this is dr. Then what we get is Q by 2 pi R ln R1 by R2 suppose. Okay. And what is capacitance? It is Q by V. So that's how there is epsilon also. Sorry. There is epsilon also. 2 pi epsilon R. That's how we get this expression. Okay. So we can directly apply this expression to find out what is L. Mu by 2 pi is what? Mu by 2 pi is 2, right? And if we are representing in microhenry, then 0.2, because there was 10 power minus 7. So this is 0.2 ln 2h by rw. You see this expression is very similar to the two-wire case, except that for two-wire case it was 0.4 ln to ln s by rw, where s was the separation between the two lines, and here it is 0.2 ln 2h by rw, right? It is just it reduced by a factor of 2. Otherwise, the expression is same. 2h is the separation between the two lines. This is 2h, and rw is the wear radius. Okay. What is h? H is equal to 50 mil. So this is, so 2h is 100, then 0.001 times 2.54. We already found out how to convert mil to centimeter. This is 0.2 ln 0.254 upon rw is 5 gauss. So 0.025 centimeter. This becomes 0.46. 0.46 microhenry per meter. Fine. Okay. So let's see the next question. This is common data for question number 5 and 6. Consider first case where the per unit length inductance of a two-way transmission line in free space with center to center separation S with equal wear radius carrying constant current to be denoted as LE1. This is the first case where we are considering a two-way transmission line separated by a distance S carrying equal current, and their radius is also equal, that is LE1. And the second case is where a single wire transmission line above an infinite ground plane at a height h carrying equal current as of case 1 has an inductance per unit length denoted by LE2. Okay. So the first case is a two-way transmission line carrying the same current separated by a distance S, and the second case is a single transmission line at a height of h from the ground, infinite ground plane, okay, carrying the same current I, okay, and the wear radius is also same, okay, so wear radius is also same. If LE1 is to LE2, then which of the following relationship holds true? See, we just discussed that for a two-wire system, what is the per unit length inductance? It is 0.4 ln S by S upon Rw. Okay, this is LE1. LE1 as per case 1. Okay, this is in microhenry per meter. And for an isolated conductor at a height of h, the per unit inductance is equal to 0.2 ln 2h upon Rw. 2h Rw. This is also in microhenry per meter. And the relationship is given Le1 is equal to 2 Le2. Le1 is equal to 2 Le2. So you can see if we equate them, then what do we get? So 2 here, 2 ln is upon Rw is equal to 2 ln 2h by Rw. 2h by Rw, right? Why these two? Because here it had 0.4 and here it had 0.2. So here 1, 2 will come, and this 2 is because of this relation. Le1 is equal to 2 Le2. Fine. 2 we can cancel from both the sides. Then what ultimately we get, S is equal to 2H, right? If this relationship holds true, then S must be equal to 2H. Then what is H? H is equal to S by 2. So option A is correct. Okay. Let's see the next question. If Rw1 is equal to Rw21, the subscript denotes case number. So these two are for case number 1 is equal to Rw. That is, in the two-wire transmission line, the radius of both the wires is same. And Rw1 is equal to 3 Rw2. So the radius of the wire in case 1 is thrice of the radius of case number 2. Okay. Where Rw is the wear radius. Okay. Which of the following is correct? Okay. So this is also very easy. Again, we will have to refer to these equations. Okay. And this also holds true here. Le1 is equal to 2 Le2. This holds true for this question also. Okay. But now the wear radiuses are different. Okay. So let's see. 0.4 ln S by RW is equal to 0.2 ln 2H, where H is the distance between the conductor and ground for the second case, by, see here it is, so RW case 1 is equal to 3 RW2. So suppose this is RW1 and this is RW2. This is RW superscript 2. Okay, this is not square. Okay, I will write like this. This, then this is 3 RW2, right? They cancel. S by RW2 will also cancel. So S by 3 is equal to 2H. Then S is equal to 6H. Okay, so option C is correct. Fine. Yeah, let's see the next question. Consider a coaxial cable having inner wear diameter of 5 gauge, shield radius as 80 mil. Determine the relative permittivity of the shield if the capacitance per unit length is 100 picofarad per meter. Okay, so till now we were discussing about two-way transmission line and single transmission line. Now we will discuss about a coaxial cable. Okay, let's see. Right. So this is the coaxial cable where this is the inner conductor and in between there is a shield and this is the outer conductor, right? So this is RW, this is the inner conductor radius and RS is the radius of the shield, right? Then of course we are finding out flux. What is flux? Flux is integral BT dot ds, where this is the magnetic flux density and ds is the surface, right? The ds is the surface. And now we are integrating from RW to RS. Okay. BT we already know, mu naught I by 2 pi r. How? From Ampere's law, right? So H dot dl is equal to I enclosed. So, and B is equal to mu naught H for free space. So from there we are getting mu naught I by 2 pi r. And if you integrate it, you will get this. And then after simplification, it comes 0.2 ln Rs by Rw microhenry per meter. Okay, this is for a coaxial cable. And the capacitance, we can also find out what is the per unit length capacitance. For that, we will have to, so these are the electric field lines, right? These are the electric field lines. And what is electric field intensity? It is Q by 2 pi epsilon r, where Q is the charge. Okay, volt per meter. Now, for finding out the potential, okay, the potential difference from Rs to Rw, we will have to do integral Et dot dl. Right, this is the voltage potential difference. And again, we get a logarithmic relationship here. Okay. And how do we find out capacitance? By Q by V. Capacitance is equal to Q upon V. So Q cancels out and we get 2 pi epsilon by ln Rs by Rw, right? Okay, so what is the question? The question is determine the relative permittivity of the shield if the capacitance per unit length is 100 picofarad per meter. So we just saw how to find out the per unit capacitance. What it was? 2 pi epsilon by ln Rs upon Rw. Okay. Yeah. So directly we can convert it to picofarad. Okay. So what we can do is we can directly convert it to picofarad as the capacitance value is given in picofarad, so it is easier. And instead of this, you can directly use this expression. This is after calculating 2 pi epsilon naught and then converting it to picofarad. Okay. Yeah. So this is 55.56. 55.56 epsilon naught epsilon yeah, so this we need to find out. Okay, epsilon r, this is the relative permittivity, this we need to find out. The other parameters are given. Ln, the radius was where dia is 5 cos, that is r where is 0.025 centimeter, and rs is 80 mil. To convert it to centimeter again, the units should be same. If r where is in centimeter, rs should also be in centimeter. 0.001 times 2.54. 2.54, right? Okay. So this value is 0.2032. 0.2032 centimeter. Now we know all the values. We know what is rs, what is rw, and C is given 100 picofarad per meter, right? C is 100 picofarad per meter. Now you can easily find out what is epsilon r. If you calculate it, this is coming 3.77. Okay. The answer is Option C. Okay. So let's see the next question. Common data for question number 8 and question number 9. Manufacturer specification of a coaxial cable is: inner wire diameter is 6 gauge, shield radius is 42 mils, characteristic impedance of coaxial line is 40 ohm. Velocity of propagation is 53% of free space velocity. Free space velocity is the velocity of light. So the velocity of propagation here is 53% of the speed of light. And all the other things are given. So R where is given 6 gauge. This is 6 gauge. Okay. And shield radius RS is also given. This is 42 mils. Okay. And characteristic impedance. What is characteristic impedance? ZC is equal to square root of L upon C, where L is the per unit inductance and C is the per unit capacitance, per unit length, of course. Okay. This is also given equal to 40 ohm. Fine. Okay. So we just saw how to find out the per unit length inductance of a coaxial cable by this expression, right? Which is coming from Ampere's law. Okay. So we have all the values, we can directly put them and we will get the inductance value, right? Okay. So 6 gauge is equal to how many centimeters? This is equal to 0.03 centimeter, and RS is equal to 42 mils. This will also be converted to centimeter. So this is 0.10668 centimeter. 0.10668 centimeter. Okay. So then this is 1.268 multiplied by 0.2. So this is coming out 0.253 microhenry per meter. Right? This is the per unit length inductance. Option A. But you see here, we didn't use these informations, the characteristic impedance information and the velocity of propagation. These two informations, we haven't used it. So where like, are they unnecessary or do we need them? So let's see. I think there are two questions. So in the next question, we will see. Determine per unit length capacitance of the line and check whether the manufacturer specification is consistent or not. Okay, so what does it mean? CE we will have to find out first. Okay, so what is CE? CE also, this is the expression, right? We just used it in the last question. Here, what you can do is, see here, uh, here they haven't explicitly said that whether it is free space or some other medium, right? But they have given the velocity of propagation, and the velocity of propagation is not exactly equal to speed of light, but it is lower than that. It is 53%. So obviously the medium is not free space, because for free space LE multiplied by CE is equal to 1 by c square, where c is the velocity of light, but here it is lower than c. The velocity of propagation is lower than c. That's why we can guess that the medium is not free space exactly. Here LECE multiplication of LE and CE is basically 0.53 c square. Okay, because 53% of velocity of free space. Okay, LE value we already know, right? LE value we already know, and CE value we need to find out, right? Mm, just put the values. What is C? C equal to 3 into 10 power 8 meter per second. Velocity of light, meter per second. Fine. And LE we just calculated. LE value is 0.253 microhenry per meter. Okay. And then if you calculate it, put all the values. Let's see what do we get. If you do c square, then in the denominator we have 10 power 8. So here it becomes 1.56 into 10 power minus 16, right? And also we have, so the inductance value is in microhenry per meter, right? So this is minus 6. Here it will be 10 power 6. So this is minus 10, 156 picofarad per meter. But you see over here, we have some answers in terms of picofarad per feet. Okay. So picofarad per feet. We will have to convert from meter to feet. To feet. So 1 meter is equal to 3.28 feet. If you divide it by 3.28, you will get something like this, 47.52. Okay. 0.52. Okay. So this is in picofarad per feet. So the correct answer is option A. Okay. Picofarad per feet. And why manufacturer specification is consistent? Because here we are getting. So when we are calculating LEC, this is actually matching with this velocity 1 by c square. This expression is matching. So here it is not exactly 1 by c square. It is lower. The velocity is lower than that. But what suppose c dash we call it. So this expression is matching. So option A is the correct answer. Another thing we can do, so if you, this is just a direct method, another thing you can also do. So mu E is equal to 1 by c dash square. Okay. So from here also you can find out what is mu and what is epsilon, and you can use this expression. You can use this expression also. Okay. Because RS and RW, they are already known. Okay. Right. So I think this is the last question. Consider the following statements. Radiated susceptibility is a near field phenomena. This is wrong. Radiated susceptibility is not a near field phenomena. It is a far field phenomena. Okay. So this we are discussing for quite some days, and we always assume that we are considering far field, right? This is a far field phenomenon. Option, what is statement B? An equivalent circuit model for radiated susceptibility is based on the assumption that length of the wire should be very much less than the operating wavelength. What they are saying? They are saying basically L, length of wire, LW is much less than lambda. So this is a valid assumption because we are assuming a lumped model, right? If your wire length is large, then we can't assume a lumped model. We will have to consider distributed parameters. Okay, distribution. Then the analysis becomes more tedious. But if your wire length is much lower than the wavelength, then uh, then we can uh, model it as a lumped. We can model with lumped parameters and we can find out what is radiated susceptibility. So this is a valid assumption. And option C, crosstalk is a far field phenomena. This is also wrong. Crosstalk is a near field phenomena. Okay. The inductive effects, capacitive and inductive, all these effects cause crosstalk. So this is near field phenomena. Only option B is correct. Okay. Okay. So I hope the numerical questions were clear. If you have any doubt, you can ask now. So do you have any questions? Okay. If there is no question, we can conclude today's session. Thank you for joining. We will meet next week.